The atomic number, which gets the symbol Z, is an important characteristic of atoms. And what scientists feel is that if you have a big collection of, say, aluminum, all of those aluminum atoms will have the same atomic number. And the atomic number literally just means the number of protons. So if you see a value for Z, that's the atomic number, all right? And that means how many protons are in that element. So if you have 13 protons in an atom, that means you have an atomic number of 13. And that will always mean that you have aluminum, because aluminum's always 13. Now, if you happen to have, say, an atomic number of 6 or 6 protons, and you look on the periodic table, 6 protons would be carbon, because carbon is number 6. And if you had only 1 proton, it would be hydrogen, etc., etc. So, woohoo, you can now look up how many protons are in each element on the periodic table. Pretty cool. Now, because no one wants to spell out aluminum all the time, they usually use symbols for these things. Symbols on the periodic table, the first letter is always capitalized, and if there's a second letter, then the second letter is lowercase. So it's AL, it's not AI, don't even go there, all right? In chemistry world, it'd be AL, not AI, and that always means aluminum, so you don't have to symbol it out. This guy Moseley was the first one to think about atomic number. He used X-ray techniques to figure that out. So a good periodic table will always have the atomic number, and it'll always have the symbol. And there's also something that good periodic tables have called the atomic weight. And we'll talk about that here in a little bit. But for right now, we're at least beginning to discern what some of those symbols mean on the periodic table, which is kind of cool. So the question might come, what is the atomic number Z of oxygen? All right, and first of all, you need a periodic table to answer this. And in class, I will definitely give you a periodic table, but if you can't wait for class, what you can do is go to mhchem.org/per-tab. This will be the periodic table that we'll use in class. And so if you look on that periodic table and you want to look up the atomic number for oxygen, what you want is that whole number right there. And if you look on the periodic table that I gave you, or your own periodic table, oxygen is number 8. That's where the O is. If you thought maybe it was the 16, that's the atomic weight, and we'll talk about that in a little bit. But for right now, we're looking just at the whole numbers, which are the atomic numbers, and that's how the periodic table is organized. So periodic table 1, for atomic number 1 would be hydrogen, and that's first, and helium, atomic number 2, would be second, lithium, atomic number 3 would be third, etc., etc. If the protons and electrons are equal, then you have a neutral atom, and that happens a lot. However, we're going to see that often you can have a system with fewer electrons becoming more positive, or more electrons, which means becoming more negative. And so I'm introducing here some new terms. I want to introduce anion and cation. And what happens is an anion is if you have extra electrons. So your atom has gained 1 or more electrons, it becomes negative, and scientists call this an anion. And we're going to see that a lot of times the elements, if they are an anion, if they have extra electrons, they get an IDE ending. Now, on the other hand, we're also going to see examples of when atoms have lost electrons, so they have more protons than electrons. Those positive ions are called cations. If you call it cations, it's okay, but it's officially cation, all right? And so in the upper right-hand corner there, you can see how sodium, we're going to see, likes to lose an electron. And so when it does, it goes from 11 protons, which is the atomic number for sodium, by the way, and a neutral atom would have an equal number of electrons, 11 electrons. It goes from that to 11 protons and 10 electrons. So it's lost an electron. And by losing that one negative one, now you have 11 positive charges and 10 negative charges. So overall, it becomes a positive 1 ion. So the sodium cation is sodium plus 1. Under it is chlorine. Now, chlorine's number 17 on the periodic table, so that means 17 protons and 17 electrons. And we're going to see that chlorine likes to gain an electron. 17 protons are still there, but now there's 18 electrons. So if you do some quick math, it's like 17 times positive 1 for the protons, plus 18 times negative 1 for the electrons. That leaves an overall negative 1 charge. So chlorine likes to be negative 1. It becomes a chlorine anion. And if you want to get technical, we're going to see that a lot of times that chlorine anion is called chloride. So the IDE can sometimes tell you that you have a negative charge. Now, if anion and cation are new terms to you, which is totally cool, just remember here, which is kind of silly, cats have paws, so cat ions are positive. Yeah, I know, I need a real job or something like that, or stay out at night, whatever. I need something, all right? But anyway, cat ions are positive. I don't have a cool expression for anions being negative, but you get the idea. There's the chemistry meme cat. We'll see that once in a while. I kind of have a weakness for those. They're so silly. But anyway, here the cat is saying cat ions are positive. And if you're a dog lover, I apologize. Now, another important part about an atom is what's called the mass number, and mass number gets the symbol A. And usually the mass value, by the way, is in atomic mass units, the AMUs we talked about earlier. So atomic mass units can be added together for the protons and neutrons to find this value. Remember, the electrons are so small, it takes like 2,000 of them to make an AMU. So we usually ignore the electrons when it comes to masses. So here's an example of a boron atom. This boron atom has 5 protons because, again, if you look at the periodic table, boron is number 5. But this one also has 5 neutrons. So the mass number, which is protons plus neutrons, would be 5 plus 5, or 10. And this symbolism right here is used a lot to represent these different atoms and what they have. The left-hand side of the element symbol, there's a lowercase and an uppercase number often. The lowercase number is Z, the atomic number. So boron on the periodic table is 5. That's why the 5 is there. The upper left-hand corner represents the mass number. So since this is boron with a total of 10 AMUs for a mass number, we would put a 10 up there. So upper left is the mass number A, lower left is the atomic number or number of protons Z. And why they do this is that we're going to see that every quadrant, every corner of the element symbol has something in it. Here's a helium example on the right-hand side. This is a helium plus 2, so it's lost some electrons. That would be the charge then. So the charge goes in the upper right-hand corner. But we'll talk about all of this later on. And if you're curious, okay, yes, the lower right-hand number will represent the number of atoms. So we saw, for example, water was H2O. That 2 goes in the lower right corner. Ah, the joys of being a chemist. Now, where this becomes really interesting is because boron actually doesn't always have 5 neutrons. Sometimes boron has 6 neutrons. So these are examples of what are called isotopes of the same element. And all elements on the periodic table have this. So it's the same number of protons. That hasn't changed, because if you change the protons, you change the element. If you, for example, added a proton to that boron 10, it would become carbon, because carbon has 6 protons. So we're not doing that. Atomic number of protons stays the same, but the number of neutrons change. And this creates what's called an isotope. And isotopes are really important. So down there below, you can see here's boron 10 that we looked at earlier, no problem. And this is boron 11. So boron 11 still has those 5 protons because it's boron. But if it has a mass number 11, then 11 minus 5, it must have 6 neutrons for it. So you can always find the number of neutrons. You can take the mass number, in this case 11, subtract the atomic number, which in this case is 5. 11 minus 5 is 6. If you did it for the boron 10, it would be 10 minus 5, or 5 neutrons. And again, all elements have at least one other somewhat dominant isotope running around somewhere with it. Some of them have many, many, many isotopes, more than 50, say. Kind of crazy.
Now, within each element, or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes.
So isotopes they used here as an example of family. Sometimes I've used isotopes as an example of ice creams. Like you can have chocolate ice cream, vanilla ice cream, strawberry ice cream. They're all ice creams, but they do have different properties. And we're going to see that the isotopes of a family can have different properties as well. Here's an example of a problem you might see. It says how many neutrons are in manganese 55. All right. And if you see that dash 55, the dash 55, that's the mass number. That's the mass. What mass number is protons plus neutrons. So to answer this question, you need to look at a periodic table and figure out, first of all, what element manganese is. Spoiler alert, manganese has the symbol Mn. So if you look on the periodic table, it's number 25 on the periodic table. So 25 means 25 protons. So 55 is protons plus neutrons. 25 is the number of protons. So 55 minus 25 will tell you how many neutrons there are. Should be 30 neutrons inside there. So you can see the utility of the periodic table. It helps you with atomic numbers, if nothing else. You can find neutrons then inside it, and this will have important values coming up. Here's an example of hydrogen, which has 3 main isotopes, and all 3 isotopes are around us all the time, especially the first 2, but a little bit of the third one as well. So hydrogen is number 1 on the periodic table, and that means that the atomic number is always going to be 1 proton, which is right next door, and that doesn't change. But what does change for the different isotopes are the number of neutrons. So hydrogen 1 is called protium. It has 0 electrons to it, all right? Because remember, top number minus bottom number equals number of neutrons, basically. Protium has no neutrons. And most of hydrogen, i.e. 99.989% of it, is this protium. This is water we drink, the ice cubes, etc., etc. However, there is a significant amount of the second isotope, which is called deuterium. And deuterium has 1 neutron plus 1 hydrogen for a mass number of 2. All right. So hydrogen 2, or deuterium, is this thing. Now, it's about 0.01%, which is actually enough that it shows up in our water. Remember, we're dealing with just massive numbers of atoms at one time. If you've heard of heavy hydrogen is deuterium, all right, and they'll do some kind of cool things with it. Notice the glass of water up above. If you make an ice cube of pure D2O, so this is hydrogen, but it's deuterium, it's so much more massive that it sinks, all right? We said that densities, the lower densities go to the bottom, lighter densities go to the top. Well, heavy water, D2O, is heavy enough that it actually sinks to the bottom. Pretty crazy. Now, there is a third isotope called tritium. Tritium has 2 neutrons and 1 proton. Tritium is actually radioactive. You don't want to have a round of it at any one time, but although there is some, it's a very, very small amount. They just put trace right here. So you don't have a lot of tritium. If you take a big drink of water, it's okay, but there is enough around that you can do some interesting things, and we'll talk about this in a future lecture. They determined the masses of the isotopes and things like that using something called a mass spectrometer. And a mass spectrometer is a really cool thing. You inject a sample right here on the left side, and it essentially vaporizes it, turns it into a gas. And then you ionize the gas sample, so it usually then has positive charges. And what they do is they use magnets. And the magnets, as you'll see in physics, or maybe you've seen it already, can manipulate the curve of the positive ions. So they constantly manipulate the magnet in order to see like what things come through to the detector there, that kind of square thing at the end. And then the results of it here on this graph will show you. So for example, in this graph, there's a lot of the 20 isotope. This is a neon isotope, but there's a little bit of 21 and a little bit of 22. So this is how they determine then that there are isotopes. It's an amazing thing, this mass spectrometer. In organic chemistry, you'll probably use it if you take it. Pretty cool. There's a great video, by the way, if you want to look up this YouTube reference that talks about mass spectrometers a lot more detail than we will. A lot of elements only have 2 isotopes, though. So like here's an example of boron. You can see there's boron 10 and boron 11. Notice that the boron 10 is a lot less abundant than the boron 11, and we'll talk about that in a second. Likewise, here's an example of chlorine. There's a lot more chlorine 35 than there is chlorine 37. And there's implications for this. This is why I'm pointing it out. At one time, for about $50,000, you could get your own mass spectrometer and gas chromatography device. I have no idea how accurate that is anymore, but woohoo! You too can do mass spectrometry in your own home if you so wish to. All right, I'd like to, but you probably don't want to.